want to just introduce you to something which is slightly different of what we have discussed up to now, but it, first of all, is interesting because it poses a very, in my opinion, non-trivial and fascinating open problem. And the reason of the interest of this problem is that you will see how many branches of mathematics come together in this problem that I will describe to you today. And so the main branches are, of course, analysis with the theory of orthogonal polynomial, but the new element which we have not discussed so much during the course is the Lie algebra, which are canonically associated to measures. So traditionally, probability measures have been studied and classified with measure theoretical ideas and tools. But now we understand that there is this program of classifying probability measures using the associated algebraic objects and structures. So recall the notations now I give for granted, except that today, as usual, we will discuss only the one-dimensional case. And what I anticipate is that in the multi-dimensional case, absolutely nothing of what I am going to say has been done. And you will see that this is also a very interesting connection with information theory, that is with the theory of complexity. So now we consider only the one-dimensional case, and the random variable, as usual, x, we denote which is the coordinate function in one dimension, and we denote p, the algebra of polynomials. Instead of taking the monic polynomial as a basis, we will take the normalized orthogonal polynomial. Well, normalized means that the norm of phi n can be either 0 or 1. So we keep the norm, the zero norm vector, and so in this language using the normalized vectors, the Jacobi relations. We have seen that the Jacobi relation is equivalent, it's just equivalent to the quantum decomposition. But now the quantum decomposition will be the symmetric quantum, not the monic one. So in the language of the number operator, we will write the cap operator as so. Well, I use the star notation, which is better. And here we put beta n. The connection between beta n and omega n is that beta n is the square root. It is usually in analysis, in the literature on orthogonal polynomial, it is taken a real square root, but any square root. Now, here we are not constrained to real numbers, but for us. So this, as you see, is a creator. It brings n into n plus 1. And this is the coefficient. The adjoint, as usual, is the creator, the annihilator, and A0 zero is the gradation preserving with the same alpha n as in the monic Jacobi relation. Okay, so these are the only new notation that we will use. This is not just because we used it in a paper. By the way, this paper appeared last year in IDA Copy, so you can see. But essentially, I will write the proofs in the notes. And now, with this notation, you see that the commutation beta square is omega n, and the commutation relation become the usual one. Is the usual one, because beta square is equal to omega. In the commutation relation, the square will appear. So now, what we want to discuss. I will try to, if I have time, at the end, I will try to comment why we want to discuss. I mentioned that in my previous lecture, our idea was to implement translations in a canonical way in the orthogonal polynomial space. But when you implement translation, you understand that you have to do with the commutation relation, and you are naturally led. So this is what we have denoted by shorthand notation. This shorthand notation. And so you are led naturally. Once you have the commutation relation, you ask yourself the obvious question. How is it constructed, the Lie algebra that we call L0 of x? X because it's canonically associated to the random variable. This is the star Lie algebra generated by creation and annihilation. Forget A0. We forget A0 because we know by the Favart lemma that every Jacobi equivalence class of measure has a unique symmetric measure, which is characterized by alpha n equal to 0 for every n. So let us restrict to the simplest case. So that is the algebra generated by, is a star Lie algebra because this is a star closed object. If you take the adjoint of the set A minus A plus, you find the same set. So the generator with the algebra will be a star Lie algebra. So the first commutation relation gives you an important information. It tells us that the omega lambda must belong to this Lie algebra. Of course, because the Lie algebra must be closed under Lie bracket. Remember, the Lie bracket are the commutator. The commutator means A minus A plus minus A plus A minus. So this is the commutator. And the Lie algebra must be closed. So you understand how we construct Lie algebras with given generators. We start from the generators, like we do here. We consider the brackets. But then, since the bracket must be an element of the Lie algebra, also the operator, the commutator, A d omega lambda must belong to the Lie algebra. Okay? In the case of the Heisenberg Lie algebra, which corresponds to the Gaussian class, if you remember previous lectures, this delta omega is the identity, which is the central element of the Lie algebra. And so, to this commutation relation simply adds a central element. And then the brackets are closed, because this commutator will be 0, and therefore the Lie algebra now is closed. So we have the two generators and the constant, which is the multiple of the central element. And we have Heisenberg algebra, which is 3-dimensional. Now, however, the omega is general. So if you remember that the action of the omega lambda on the phi n the action of the omega lambda, in fact, we can say omega lambda is even simpler. Omega lambda on the phi n is omega n phi n. Then you see, and in our definition, you have that A daga, A minus, we are doing A minus, phi n is beta n minus 1 phi n, okay? So you can compute easily this commutation relation, because you have A minus of any function of lambda. In fact, here we can write any function of lambda, not necessarily omega. This is correct. So if you apply to phi n, phi tilde n, we obtain that this gives Fn, and A minus gives beta n minus 1 phi tilde n minus 1. And if I compute in the other order, A minus applied to the same vector, this gives now beta n minus 1 as before, and the phi n minus 1. But now F lambda acts on phi n minus 1, so I have F n minus 1. Okay? So we have A minus F of lambda is if we compute the commutator, on this phi n, you have to subtract the 2, and you obtain phi n minus fn minus fn minus 1, and these are the same phi n minus phi tilde n minus 1. So this gives the commutator that we want.
And the beta n minus 1.
What?
Beta n minus 1. On the right hand side.
The beta must be somewhere. Beta n minus 1. But the important is that it is the same, because when you write in operator language, you find the commutator in our convention. You see, because I am acting on n minus 1, so this will become this. If I take this df lambda, by definition means f lambda plus 1 minus. This is the definition. Okay, It's the forward shift from the right. So now,
Yeah. So on the left hand side you have phi n tilde, and on the right hand side is phi n minus 1.
this is phi n minus 1. Comes f lambda a minus, is phi n minus 1. And this is a minus, which is this term, which gives me a phi n. So this gives the subtraction. This is the same. Or not?
So on the left you are acting on the vector phi n.
And also on the right, I'm acting on the vector.
On the vector phi n minus 1.
And the phi n minus 1.
So it's not something like just a scalar times.
No, it's A minus is the commutator now. Operator will be right.
Because right, this is the, you are correct. This is, I forgot to write, this is not the correct formulation, because it's not so simple. This is a minus on phi n tilde. So this is the correct formulation.
Also.
And a minus. This is in fact, this will be very important, the a minus here. If I have done now, I think it's correct.
Yeah.
Because I'm acting on that. Yeah? So this will bring me to, and f lambda plus 1 will give me n, and minus 1 will give me n minus 1. So this is, but this is important. Why? You see, now you see something which is this notation is typical of associative algebra. The product doesn't exist in Lie algebra. But what does it mean? In fact, we are not working in an abstract Lie algebra level. We are representing this object, the generator of the Lie algebra, in the Fock representation, in a very special representation. Okay, so we are asking ourselves, what is the minimal subalgebra of the whole algebra, star algebra of a jointable operator on the Fock space, pre-Hilbert space, which is closed under Lie bracket and which contains these two operators. Okay, so we have found that first this Lie algebra must contain this operator. But now we find that it must contain also this operator. Okay, so it must contain the commutator. And I compute just another one to give you the feeling of the induction. It must compute the commutator of a minus with this, here I should correct. Here we have found a general commutation relation, but in order to conclude that it belongs to the algebra, we must apply it to this operator. So we must say that A minus d omega lambda. So you see now this plays the role of f lambda, but I have d f lambda here. So it comes d square of omega lambda times A minus. Okay? It's clear? This identity, we did the calculation for an arbitrary f, but we know that this function of lambda must be in the Lie algebra. Therefore, we conclude that this commutator is in the Lie algebra. Okay? And now we procedure. Since this is in the Lie algebra, we iterate and we have that A d square omega lambda times A minus also must be in the Lie algebra. But by the Leibniz derivation property of commutators, you know, and since A minus commutes with A minus, you know that this is equal A minus d square omega lambda times A minus. But now we use the fact that this commutation rule is true for arbitrary function of lambda. So it will come the partial difference of this operator, which is the cube, but now times A. So this will be d cube omega lambda times A minus but square. And now you do by induction. Okay? So if you suppose that, so you see the scheme is A minus power n, derivative operator, the finite difference operator, power n plus 1. So if we suppose that the algebra, the element d n plus 1 omega lambda A minus n belongs to the Lie algebra, so A minus commutator with this must belong to the Lie algebra. And with the same derivation property, we obtain that A minus d n plus 1 omega lambda A minus n belongs to the Lie algebra, but this, now we have the arbitrary function. And we know the commutator is this. So another delta appears. And we have delta n plus 2 omega lambda A minus, and now 1 minus more appears. So by induction, all these elements belong to the Lie algebra. Therefore, if we can prove that the sequence of these elements are linearly independent, or even they will be linearly independent, we will see, but they contain a subset which is infinite